Okay, so in the previous video that I might have posted, I don't know if I've done them in order yet, I filmed for single A-level maths, the first year, the year 12 content in other words. Basically, I want to step this up now. I'm going to step it up into the scalar product. Now, I've already drawn a diagram to basically show you what I'm going to do. But essentially, we're going to find the angle between two vectors. Now, the angle between two vectors, you might recognize what's going on here. We basically need three things. We need OA, OB, and AB. Now, AB is OB minus OA, so we can find all these bits. So I've drawn the diagram there. So O to A. Well, what is O to A? Well, in component form, that's 3i plus 5j. O to B, well, that is 7i plus j. Right. Make sure you all know your vectors and stuff. Well, what's AB then? AB is OB, take away OA, so that's 4i. Now, we've got 1, take away 5, so it'll be minus 4j. Okay? Now, we're going to look at the cosine rule with this. And the cosine rule will actually work. So, the cosine rule says that AB modulus squared is B squared. So, I'm going to use OA plus OB squared. So, B squared plus C squared, okay, minus 2 lots of OA and LB multiplied together. And modular sines times cosine of the angle. So rearrange for cosine. So cosine theta is equal to, so rearranging that, we get OA squared plus OB squared, take away AB squared over 2 times OA times OB. Yeah? Should be getting that. All I need to do now is substitute in. Up to the calculator, we need to find the moduluses of each of these. So the square root of 3 squared plus 5 squared was root 34. 7 squared is 1 squared, well I can do that in head, that's root 50. And 4 squared of 4 squared is root 32. Okay, so all I need to do now is apply these into here. So I'm going to get root 34 squared, so it's going to be 34, plus that will be 50, take away 32 over 2 times root 34 times root 50. Okay. Calculate it. 34 plus 50, take away 32, divided by 2 times the square root of 34 and times the root of 50, which will be 13 times root 17 over 85. All you need to do now is inverse cosine of the answer. Then make sure you calculate it in degrees. That would be a good start, wouldn't it? And you get inverse cosine of 13 square root 17 over 85, which is 50.9. Yeah, to 3 significant figures. So we're using the cosine rule here in order to determine the scalar product. In a sense, we've got half the job done. The other half of the job is actually defining the scalar product. This is an example of finding the angle between two vectors. So we're going to use the idea of the cosine rule in order to basically solve this. Now also, I want to point out, you might see in textbooks the scalar product also be known as the dot product. Now, I don't know if your exam board mentions it, it might put it in a little box saying this is also known as the dot product. That's still fine. And actually on your calculator menu, if you go to number 5, define a vector in 2 dimensions, you could have 2 in, I don't know, 0, 0, for example, vector calculations. Into options, keep scrolling down, you'll find option number 2 is the dot product. So you can find the dot between 2 vectors straight on your calculator, even the angle as well, and the unit vector. If you're interested, your calculator can do that. Okay, so that is how we can find the angle between 2 vectors using the cosine rule. Okay, so I've just spent about 5 minutes trying to write out what's going on here. So I've got, in 3 dimensions, A1, A2, A3 is point as a coordinates of A, and a coordinate of B is B1, B2, B3. Okay, kind of makes standard. So basically, subbed it into the cosine rule, which I just proved a minute ago. I've subbed it all in, and I've got to this. It looks pretty messy, it took forever, right? Now, I'm going to jump another line, because I'm going to expand all that out in one go, because I know what the result should be. You get 2A1 B1. A should be normal, not a subscript. Okay, plus 2A2 B2 2A3 B3. Okay, all over 2 times the modulus of A times the modulus of B, which is, because your 2's always cancel out now, so I get with A1 B1 plus A2 B2 plus A3 B3 all over modulus of A times modulus of B. Okay, now what is A and A1 B1, A2 B2, A3 B3? Well, what is that? Yeah, well, that is literally A dotted with B. Yeah, that is A1 B1, A2 B2, A3 B3. Added all them up, yeah? So I can sub that into here. So I get A dot B, all divided by the modulus of A times the modulus of B. Okay? So cosine theta equals that. Okay? And that is where this scalar product / dot product is coming from. Okay? It's really hard to prove when you're not got a lot of board space, so make sure to push the channel because I can get a bigger board and I can actually do some bigger proofs. Because I really want to look at some big proofs in there. So if you want to have a look at some bigger proofs, then hopefully make sure you really like and subscribe to the channel if you like what I do here on the channel. So we'll have a look at an example now of using the scalar product, and then we'll quickly explain it. Okay, so example coming up next. Okay, so let's have a look at this example. We've got it in 2 dimensions, doesn't change the process, still works the same. So we're going to find the angle between 3,7 and 1,5. Right then, how do we do this? Well, we just need to sub straight into that equation of the product at the top. There's cosine theta is fully enough equal to, well, it's that times that, 3 times 1 and 7 times 5 added together, divided by the modulus of each. Well, the modulus is the square root of 3 squared plus 7 squared times square root of 1 squared and 5 squared. Calculate it. Make sure you're in the right mode. 3 times 1, okay, add 7 multiplied by 5, all over the square root of 3 squared plus 7 squared, multiplied by the square root of 1 squared plus 5 squared, and the top fraction will give you 38. And the bottom gave you, what was that? times root 377. Okay, well, theta then is just the arc cosine of 38 over 2 square root 377. Which is about 11.9 degrees. 2, 3. Okay. That is how we can use a scalar product on the angle between these two vectors.